So thanks everybody for coming today, being here this afternoon. So we're going to talk about cloud-native security patterns. So cloud-native systems are generally built as containerized microservices that we run on systems like Kubernetes, Mesos, and other orchestration and distributed management tools. Compared to monolithic services, we kind of distribute the problem. We have to approach security in different ways. We can inject security in ways that we can in a monolithic type of architecture. And with cloud-native systems, there's a lot of opportunities, but there's also a lot of ways we can kind of go wrong. So today we're going to look at some of the common patterns that are implemented in cloud-native systems, and some of the programmatic patterns and higher-level tools that you can use as well to secure your infrastructure. So we're going to focus on some of those patterns. I'll talk more today about Kubernetes, Docker, and AWS, just because I work with those on a regular basis more than others, but I'll throw some GCP references in there as well. And we're going to look at things like how to implement secure multi-tenancy. So lots of times we see application teams providing a multi-tenant environment, which is very different than if you're running a monolithic application in, say, a single virtual machine. So we're going to take a look at how do we actually lift the stacks we have now into a cloud-native world. So about myself, CEO at Invisium, I've been doing that for a couple of years now. New Yorker trapped inside the DC Beltway. I actually learned how to drive in New York, which means I learned how to use things like my horn and turn signals. Sorry about that, everybody else in America. And I'm not a big Texas sports team. Any Cowboys fans in here or anything like that? Did you watch the Redskins game last week? Because it was one of the few times I was actually cheering for the Cowboys in my life. And they failed. That was bad. Yeah, so I do a bit of development, Go and Scala. Some days my job is spreadsheets and meetings, but I usually try to find ways to get into a code editor throughout the day. So cloud-native systems. Generally we're running containers, right? So we're not often running big virtual machines. We take advantage of modern architecture that allows us to do things like scale horizontally, build resilient systems that do self-healing. And to do that, we want to be able to scale kind of horizontally, be able to launch containers at will, kill them, and so on and so forth. So containers are a good way to deploy systems in a cloud-native world. We're generally building things as microservices, so we're not often building monoliths, but that's not to say that we can't build monolithic applications on a cloud-native stack. It's just not kind of done as much. Or you'll see it where people are decomposing a monolith, and they'll do it, one piece at a time. So you may see kind of that, where you will run some kind of monolithic stack. But generally, you have some sort of polyglot type of data persistence. You don't generally have like a single, MySQL, right? One service may want to use something like Cassandra. Another service wants to use DynamoDB. And so generally you deal with a lot of different data stores and your data goes in a lot of different directions. So you have to think about the life cycle of those things, access, so on and so forth. With regards to just dynamically orchestrated systems, so we're going to run things on something like Kubernetes. We're not going to run containers with like a shell script and a loop, right? So these systems are heavy duty. They handle things like resiliency, different deployment strategies, scheduling, and a lot of hard things that you wouldn't be able to kind of manage on your own. Compared to the way we built software before, things are very declarative. So we have things like YAML files, and we have infrastructure as code, so on and so forth. So things are declarative, and we expect that there's going to be automation from end to end, right? So not necessarily putting humans in the mix as much. But at the same time, our architectures describe themselves. We want to have the ability to get data and telemetry from events. So a lot of different things happen, and we want to be able to respond to those things accordingly. Things like circuit breaking, when we know, for example, a service has gone down and we need to kind of fail over. And we can implement things like circuit breaking with these platforms as well as in our applications. And things like resiliency are extremely important, right? So you shouldn't really be planning for your systems to never fail. You should embrace things like failure. You should expect failure to happen. You should anticipate the ways failure is going to happen. And building on a cloud-native infrastructure definitely makes you think about resiliency, but gives you a lot of different strategies for how you can also be resilient. And whose job is it anyway? What you generally see is a couple different kind of models in what I've seen. You'll have platform teams, so bigger shops that are going to do multi-tenancy, where they're pretty much moving their entire stack onto something like Kubernetes. They're generally going to have a platform team that's going to handle some things, including like the control plane, setting up the infrastructure, basic things like RBAC and authentication, and then those things become self-serviced by the teams, right? big kind of theme is everything needs to be self-service. So we can delegate rights down to teams, right? And we can give them segregated kind of environments where they can run prod environments, they can run dev environments. But we want to definitely try to enforce multi-tenancy. That definitely goes wrong, I've seen a lot of times, right? So depending on the cross-cutting concerns and who's handling what, especially as people migrate to kind of modern architecture from the way they've been doing things, something always falls through the cracks, and what you end up finding is that somebody didn't do something somewhere, whether that was something you should have put in a Docker file, something you should have configured at the control plane level that should have never happened, or something you could have configured like at a pod specification, right? So multiple layers and different people handling things. And isolating containerized workloads. So this is an example of Kubernetes and its control plane, but these concepts are the same mostly in cloud native. So for starters, we're generally doing most control and operations things over the network. And more often than not, we're using REST APIs to do that. There's also things like gRPC, and we can work with RPC as well. But generally, when it comes to things like Mesos, Marathon, or Kubernetes, we're exposing most things over an API, which allows you to spin up containers, kill containers, run commands in other containers, and so on and so forth. So the API is definitely a juicy place to attack. You generally have some type of persistent data store for a cluster to represent its state. So in Kubernetes, they use etcd as a key value store. And etcd definitely has some security issues if you don't configure it out of the gate. More often than not, more of the deployment tools nowadays, they do build some security opinionations in there, not exposing it on all interfaces, ensuring that there's mutual TLS to authenticate between peers and as well as the API. But there are some deployment tools and script I've seen out there that just kind of strip these things down. And I've seen teams just kind of pull these things wildly, and they end up having a key value store exposed in their network that pretty much controls the cluster state. And you could just basically connect to that without authentication, right? And that's something you could do really easily. So anything programmatic you do at that point is moot because you're just pretty much game over at that point. An interesting thing is that we implement controllers to do a lot of things, to manage different resources, to be able to react and do different things within the cluster. So the controller manager works with the scheduler to figure out where to essentially end up deploying these resources within our cluster. So our containers actually run somewhere down there at the end of the day. So at the top is our control plane. And these, whether it's Docker Swarm, Mesos, Kubernetes, you're generally working with some sort of control plane. And then we dig down to the container level. So we have a lot of different things to consider here. We want to keep you in the container, right? So especially in a multi-tenant environment where you can essentially jump out. If you can get out of that container and you can get onto that host, you can pretty much attack anything. So we want to think about, can you attack other containers? Are there things like network ports exposed, right? So we can expose a container as a service, and then even if we have it in a namespace, all containers can pretty much hit it because it's just an IP table is ruled open at that point. So at that point, we don't really get great network segmentation, and containers by default don't generally have strong egress. They have better ingress. So we want to think about how do we keep you in the container, and one thing is obviously egress rules getting out of containers. We definitely don't want you to be able to attack different components. So the kubelet, for example, in Kubernetes has had some issues over the years. Essentially, if you can attack the kubelet, then you can try to attack things upstream, manipulate other containers that are running on that node, so on and so forth. So you definitely want to keep those things safe. And you most certainly want to limit what you can do at the API server. So the API server is kind of the kind of gateway to everything else, right? So if you can impersonate or elevate privileges at the API, you can do a lot of things, right? So you want to make sure that you're giving containers minimal privileges out of the gate, so you don't want things running as root. You want to limit containers sharing the same accounts because you break down a lot of walls at that point. So as we mentioned, the control plane and core components, this does pretty much all the brains and work of the cluster. And if we get access to it and we can compromise it, then we can pretty much take things over. So I've seen people do a really good job at isolating network access to the control plane. I've seen environments where people could talk to control plane from printers and guest Wi-Fi network. So kind of pick your poison at that point. But one of the nice things that if you are using one of the managed services, generally they're abstracting away a lot of the control plane stuff for you, which means they're hardening it for you, they're updating it for you, and they're restricting some level of access to what you can actually do there. So if you're using a managed service, then you kind of do things a little bit differently. One of the core things, though, is working with the Reconciler pattern. So basically what ends up happening is that we always want to move our cluster towards a desired state. So as our configurations are declarative, and we can say this is what we want our cluster to look like, right? So we want, when this container is deployed, we want it to be running with these attributes, annotations, and settings at runtime. And if something changes in the specification, then we want that environment to match that almost instantly, right? So that's kind of the concept. So if we make a change and we change something in a container's deployment in the pod specification, it's going to immediately respawn that. In some cases, obviously, if we've met all of our security constraints and stuff like that, but this is a pattern that's core to kind of how Kubernetes works, and we can obviously use that for security purposes, right? Quick patching, so we're not thinking about these long life cycles of containers. Assuming we're working with a fairly stateless container where we don't need to think about, so if we're running databases, then we have to think about state. If we're running things like message queues, then we really need to think about state. If we're running a really thin MVC app that's not doing things like caching and stuff like that, then we can be a little bit more flexible with killing those things, right? So if we adopt this pattern here, then we can use that for security, and compared to how long it may take in some environments to actually push changes in a maintenance window, right? We could do things at the speed of light. And with Kubernetes, we could also do different deployment strategies, blue-green, AB, and stuff like that. So depending on how you deploy applications, you can tie those practices into kind of these core patterns that are provided for you out of the box. So basically something I should kind of throw on you guys is containers aren't really great sandboxes, as if that kind of wasn't clear from the first couple slides. So as we talked about, we share host resources. And basically, if we overprivilege our containers, then that translates to we're overprivileging them in some cases on the host itself, right? So root inside of the container has the ability to access root namespaces, control groups, and things like that on the host. So if we aren't careful, we share too much, right? Because Docker, Rocket, LXC, similar container technologies for Linux like that, they rely on standard Linux facilities like control groups and namespaces, right? Which have been prone to implementation issues over the years. And what we end up doing is relying on things like SATCOM quite a bit to limit the syscalls that we can access. So Docker has a default SATCOM profile that blocks a bit. But then, I know many people that also run containers that don't actually implement SATCOM, which means you get none of those inherent controls. So when we rely too much on rule-based security controls, we shoot ourselves in the foot. And here's an example. If you don't believe me, container escapes happen. Virtual machine escapes have happened a lot over the years as well, right? We shouldn't not use these technologies, but we should understand, in our threat models that these are realistic threats, right? That these things are going to happen at some point, potentially. But essentially, if you look at most of the kind of the characteristics of container escapes, you find that either there was an object that wasn't properly namespaced, the containers had more capabilities and they weren't dropped. You had the ability to manipulate the container's identifiers somewhere through the container spin-up lifecycle to assume greater privileges, somewhere between building and running. And generally, these things kind of go back to the same kind of core issues. But we should understand that certainly it's definitely possible to get out of a container. So here's our gateway drug. Here's a Docker file, right? Here is a container image that we're extending from Golang 10, 1.10.2. There's me, the maintainer. We can set user, but we can also, at the container orchestration level, shoot those things down as well. We have some commands we'll run, and then we have some code that we move over. What ends up happening there in reality is that there's actually a fat daemon running on the host that's spawning those containers. So in the way Kubernetes works, it interacts with the kubelet. When we looked at it right here, which is right above the container runtime. So essentially the kubelet is being told by the schedule that it should run things, and then it runs things. That's maybe the easiest explanation for that. So it's a fairly dumb process in that regard. But basically that daemon is what's managing that. So if you can pretty much control the daemon, then you can control the containers on that host as well, right? And you can assume some of those privileges. So you can move laterally, and in some cases, potentially elevate privileges inside of the cluster, depending on service accounts that are being tied to those containers and whatnot. And we have different ways we can isolate our containers. The traditional way with, and so by the way, I'm not talking much about Windows because I don't do much with Windows. But if you're doing things on Windows, the TLDR is you can use Hyper-V, and you at least get basically like the hypervisor level of things. But in a Linux world, we can work with C groups and namespaces, but we know there's a lot of implementation issues, ways to jump out of there. Cool project that I've kind of been following, playing around with, is gvisor out of Google. They've implemented a lot of kernel stuff in user space land, and including a lot of the Linux syscalls, but not all of them. And so pretty much you have that, essentially one, limiting the privileges you can assume on that host, but also giving you a limited set of syscalls and things like that. So it definitely provides a better isolation model in my opinion, but it's definitely a young technology. And you can go back to the hypervisor and virtual machine way based to doing things. Kata Containers, which is based on Intel's Clear Containers, uses Qemu Lite, and you essentially run Docker inside of a small stripped down virtual machine. So it gives you that, obviously, wrapper you get around a hypervisor and a little bit more, but also you have the performance hit and resource utilization of running a hypervisor around your containers. So you also have to consider that as well. Not everything is free in this world. And in terms of how the container runtimes stack up, you find that Docker kind of gets most things right compared to some of the others. They have strong defaults for things like SATCOM and AppArmor and capabilities and things like that, but you can turn those off just as easily. I can't stress that enough. Like I like the things that the container runtimes give you, but I see more often than not people don't get the full benefit of those things. So when you're managing your base containers, make sure that you're first and foremost using containers that actually do have support for AppArmor, SecComp, SE Linux, if you want to use those things, right? So just because you're pushing them from Kubernetes, saying like, you know, thou shall run SecComp, if it's not supported inside of the container, then it's not actually going to give you any of those benefits, right? So you do want to make sure that you're using images that support those things. Something I see people do a lot where they lose control was use like image latest tags, right? Instead of actually pinning to actual specific versions. So that's one thing that you should definitely consider, is always using tag versions. And if you're using things like you know, Docker Trust, Google's binary authorization, then you can also do some level of attestation and trust and signing of those to ensure that you're only running trusted images. But that's maybe another slide if I had it. I don't have it in here. So SecComp, for anyone that's not familiar with SecComp, and these are things, by the way, that traditionally, like, we haven't talked to our like Java developers about things like SecComp and syscalls, right, and how to run SE Linux properly and constrain things. And honestly, you can kind of keep some of these details out of your developers' hands, my take. But SecComp allows you to basically limit and filter a bunch of syscalls, which basically translates to things that aren't gated by dropping capabilities. You can also block with syscalls. So if you were to say, for example, do capability dropping in conjunction with SecComp and syscall filtering, then you can get a little bit more granular for kind of attack surface reduction. And Docker, again, has a good profile, but you have to have support. And if you do have support, then by default, Docker will run with that profile for you. So if you support it, it's like a quick win, and your developers don't have to do anything to get the benefits of it. With regards to AppArmor, so there's also a policy for that as well that Docker runs. AppArmor gives you the ability to do a little bit more. So you can work with things like capabilities, but you can also deny more granular access to resources like files. But again, within AppArmor, there's also a strong Docker default, and other container runtimes do have good ones as well. Capabilities are an interesting one because we generally overprivilege our containers like crazy, right? So who thinks like their Tomcat container, who thinks Tomcat needs to run with root? Anybody? Okay, cool. You all have jobs still. But I've seen this like time and time again, right? And you kind of shoot people down. It's like, so you either blame yourself for giving people the ability to deploy that way, or blame them. But honestly, I would blame you for allowing them to do that because you have quite the capabilities in things like Kubernetes, for example. Docker has the ability to drop these things as well. And you can manage them with Swarm. So more often than not, this is just a lack of understanding more than anything. And again, Docker does drop these down significantly. And by default, you're going to get these. What you don't always get is SecComp if you don't have support for that. So if you don't have SecComp, at the very least, you do get gating of some of these things. If you actually drill into the syscalls, you find that some things kind of bubble up to things like capsysadmin and other capabilities that are subset, that the syscalls end up being a subset of, right? So depending on, you either have a lot of security or just enough. And with regards to privileges, right, so here's an example of dropping a bunch of capabilities, and this is what you need to run ping. It's like the ability to use raw sockets, right? And you can essentially drop all the capabilities and still run this and do exactly what you need to do in that container, but nothing else, right? And that's good, because honestly, we want to limit what our containers can do. The problem with maintaining some of these things is that, one, our applications change. Two, we need to profile our applications to figure these things out. So there are tools, for example, if you Google like AppArmor or learning, there's different things built in AppArmor tooling to basically look at a set of processes and build AppArmor profiles for them. So it looks at which capabilities it uses, which files it accesses, so on and so forth. And you can build automated profiles. They wouldn't be as tight as if you built them by hand, but they're better than nothing, right? Because not everyone in your organization is an AppArmor expert. Not everyone in your organization understands, the nitty-gritty about privileges and capabilities. Something we could do is work with user namespaces in Linux. So this is something that modern kernels support. And Docker supported for a little bit, but you haven't had upstream support in the orchestration platforms for a bit. So basically, if we enable the feature gate in Kubernetes there, experimental host user namespace defaulting gate, that essentially allows us to end up doing user space remapping of things. What does that translate to? Is the fact that instead of running with an actual user ID that has relevance on the system in any way, we're running with like a really high UID user that's not going to have like any privileges on that system. So worst case scenario is if you can basically get an impersonation of that user and do things on the system, you're going to be restricted by what they can do in terms of discretionary and mandatory access controls. So it gives them the ability to at least kind of nip that coming out of the container. Newer thing that's kind of getting better support, but it's not something that's well supported everywhere, is rootless containers. And basically we want to run containers that essentially can't run root. Runc and some other ones do have some support, but what's been limited, so if you look, for example, on like GitHub and look for like rootless, like Kubernetes, rootless Docker, like you'll find a million open issues that people have been working on for years, and new ones that pop up, right? It's really hard. Because you have to think about what happens in the container, has to be replicated on that host. And then within a cluster, you also need to replicate that between nodes, right? So it's fairly complicated when you think about what happens at the container and then the runtime and then basically in the distributed manner, right? So it's fairly complicated. Kubernetes has some support in 1.12 within the process mount security context attribute. If you flip that, you do have the ability to work with some of the rootless container stuff, but yeah, use at your own kind of discretion because it's fairly new. And if you notice, and you've been working with Kubernetes for a while, you see things like experimental and alpha and beta kind of thrown around like just anything. So yeah, take that with a grain of salt. No new privileges. So this is one that's been supported in kernel for a while, but it limits the ability for a process to assume new privileges. So you can break, the ability to elevate with like set UID and set root ID binaries. So basically the idea there is that if you were to run a binary which had like the set UID flag for root set on that, you would essentially run still as your effective user ID. So you wouldn't assume root privileges. And you can break a lot of attacks like that, right? So a lot of times you find, people leave. I mean, this is if you're an attacker that's on, Linux box, that's one of the first things you look for, right? Can I find binaries that allow me to elevate privileges? So you can limit essentially the ability for an attacker that gets onto your container, SQL injection is going to happen, some kind of RCE bug is going to happen. Like in my world, I assume somebody's going to get into that container and own your application, right? It's what do I do from there and what do I limit you doing within the cluster that matters at that point. And if I could restrict your ability to basically assume privileges another way, great, right? Take that off. Authentication, right? So we've talked a little bit now about what happens at the container level, and it's very important to keep you inside of the container. But it's not always possible, unfortunately, right? Because the containers have the ability to interact with the cluster, so on and so forth. So not always feasible to keep you really constrained because there's things you're still going to need to do in a real world. But we need to do strong authentication. So our applications, our containers, they authenticate themselves to the cluster to do different things. We also have users and developers, right? So we're going to give people access to deploy things, to manage the cluster. So we're going to give them access, which translates to API access. But essentially each service we run ends up getting its own service account. So it runs with its own UID essentially at that point. And that actually gets us a token mounted within that containers etc. That allows it to basically authenticate to the cluster using that as a bearer token, right? So sometimes we have to think about the kind of authentication and how we're sharing credentials between containers. So if we're not setting explicit accounts, then they're defaulting to like a default account, right? So it's definitely part of an account management strategy. So yeah, in each namespace, by default, you get dropped into, so when you create a new namespace, there's a default account. If you create a new application and launch a pod without setting a specific account, it defaults to default. And if you create a new one, then it defaults to default, right? And so now you have this problem where you have dozens of applications that can suddenly call API on behalf of each other, pull down things like secrets, crypto keys, I mean, all the stuff that you'd essentially want to have, some separation between, right? So even though we're doing things the right way, we're using secrets management, we end up having implementation flaws that end up just kind of undermining that whole structure. And even if we're blocking ingress, for example, network access to a container, we can still attack them through the API, for example, right? So if we're sharing things like credentials, there's different endpoints that we can use to essentially send commands. So from one container from another, without network access, we can do that, right? So we didn't have network access in, but we had API access. And on that actual kubelet, there's a couple different services that are running. One of those is to receive things like commands and route them to the appropriate container. So that's something like as a developer or even like a cluster administrator, like you can't shut off. That's just behavior, right? So if we, again, don't do privileges right, then we open ourselves up to that attack as well. So we certainly want to make sure that we're doing that. So we always want to create a unique service account per pod. And that's the command right there in Kubernetes land, create service account, that's one. You specify the namespace because any service account does need to be namespaced. So those aren't like a custom level resource. And you create that within a namespace and you create your pod. I don't know how well you can see that in the back, so let me just blow that up in the wrong direction. Almost. There we go. Hope you can see that a little bit better. But essentially at that point, we're just specifying that's the actual service account we want to use. And when that actually happens, it's going to get its own service account token that's going to be unique, and it's not going to be able to impersonate other accounts. Now, if you've given that service account, for example, like cluster admin privileges, well, that's your own fault, right? By default, it's going to get access. Once you've turned on things like role-based access control, it's going to be restricted quite a bit, right? So RBAC is one of those things that's cumulative, right? You can add but not take away the way it works. And we don't want to share things from the host. So this is another way you can poke holes in things. You can share mounts. You can share access to be able to talk to different network paths, IPC pipes. So generally you want to avoid sharing any of those things at all costs. And one of the things we can do inside of a pod security policy is actually set some of those. And off the screen again. And I'll just, if you can see, I know you can't, but basically there we can set things like host network false, host IPC false, host PID false. And basically at that point we're saying within a policy that we're going to apply when containers are admitted to our cluster, we're saying that you actually can't assume any of those things, right? So this is one of those things that you'd play whack-a-mole if you kind of try to do it on every container you launched. So as a preference, I'd rather do this in kind of a centralized manner. So those are generally things you'd want to kind of adopt policies for. Now in reality, you run, most cases, multiple policies to do that, right? Because you have different containers that are going to need to run with different levels of privileges. So does anybody run any of the commercial kind of container security tools that force you to run things like capsysadmin and ptrace and other really, really privileged things? So I've actually seen groups that have implement multiple pod security policies. And you can, if you don't do those correctly, overcast those where potentially containers you wouldn't want to be getting those privileges would. So definitely a thing to consider. Authorization, so we've authenticated you, we know who you are, whether that's your account to authenticate to the API, whether that's the service account that you're using to do things, we know who you are. So once we know who you are, we have to figure out and tell you what you can actually do. So when we think about subjects, we have generally users, we have service accounts, and then we have groups that we can put them in. And it's important to understand what they can actually do. So Kubernetes, pre-role-based access control, and if people weren't using like attribute-based access control, was a real shit show, right? So pretty much you can do anything you want, right? And it was really hard to limit what people could do. So RBAC came along and it's there, right? So a lot of implementations turn it on by default. So if you build, for example, with like kubadmin, and it's like it has RBAC emission control turned on, or authorization mode, sorry. And it allows us essentially to limit what individual users and services can do. We can do things at a cluster level, right? And sometimes I see people just get lazy and they're like, well, screw it, I give everybody cluster level access to stuff. And in reality, we, at that point, have already kind of shot ourselves, right? Because we have namespaces and we have other layers that we can do some segmentation at. So the best thing we get there is some control of blast radius. So imagine we have, say, 20 applications running on this multi-tenant kind of infrastructure, right? Or 20 different systems running in their own namespaces. And if we're granting people only permissions at the namespace level, the worst case scenario, one of those accounts gets compromised, or somebody gets their service account token, and they're only going to get the ability to do things potentially inside that namespace, right? So we've limited the blast to our other applications in that multi-tenant environment. What you end up seeing a lot of times is people will grant things cluster-wide. So the first couple people that need to do any kind of like ops type of stuff or set systems up, right? They get cluster admin, no questions asked. They get like SSH into like a master node and all these things they shouldn't get. But this is one of those places you generally want to start as low as possible, like anything, authorization or role-based access control, because you can overdo it and you can give people the ability to pull secrets, control services that they would have no other business doing. And it's fairly easy, so everything is going to be some kind of YAML file, or you can even use JSON if you like that. But basically on the left-hand side, we create a role. So we create a role in the production namespace, and we say that role has the ability to access one API group there, which in Kubernetes, if it's blank, that's the core API group. So that has all the primitives like containers, pods, secrets, and the things that have been around for quite some time. And we're giving it the ability to only do essentially read-only type things, right? So get, watch, and list. We're not giving it the ability to do deletes. We're not giving it the ability to do patch, put, and stuff like that. We're giving it only the ability to read things at that point. On the right-hand side is where we actually bind it. So if you create a role, it has no bearing because it's not actually applied to a subject. So on the right-hand side, we're applying that to a service account and within the production namespace. So again, if you recall, service accounts are always a namespace thing. And we're giving that service account only the ability to do those things inside of that one specific namespace. So if that service account was to be compromised, then, obviously that's production in that example, right? You're probably hosed anyway. But at the very least, it would be production of one application or system, and it wouldn't be basically the whole environment at that point. So pretty powerful. So within Kubernetes, everything works as a controller. And this is something that's a kind of a cloud native core pattern there. So we end up creating controllers for different things. And then those controllers will watch what's happening, and those controllers will do things very focused on a specific type of resource, right? So in Kubernetes, you have a controller that handles secrets, deployments, and all the different types of resources and workloads. They're very specific, right? And they understand the behavior of those particular objects better. And what they essentially allow you to do, though, is in Kubernetes land allows you to read the object specification and mutate its status or do things like enforce security controls. And an example of that is the emission controller. So what it ends up allowing you to do at the time of emission is check what the container is set with regards to security settings. So is it running as root? You can set things, enforce it to use a specific SATCOM profile. You can ensure that you can't elevate privileges. There are things that if you were trying to manage these on an application by application basis, you'd fail because things move way too quickly and you're a human and surprised you get in the way at this point, right? So these are things, honestly, in terms of a control that you're much better off using a controller to do that. And the controller essentially is going to pretty much get hit every time you're trying to emit a pod to the cluster. And it's going to check the pod's specification, determine if it is secure, and it's either going to mutate some things or it's going to reject it from getting emitted to the cluster. which is pretty cool. PSP is one of those things you generally turn on in most distributions. And interesting thing, kind of some rules that I've seen people confuse themselves with. So you can have more than one pod security policy. First off, it's going to take the ones that aren't going to mutate things. If not, then it's going to go alphabetically, right? So if they're kind of similar, then it's going to go in alphabetical order. And if it's a pod update, it's going to reject things if you actually have to mutate it, right? So new pod, sure, but a pod update, then it's going to work differently. And these are the primary things you can control using a controller, for example, pattern and enforcing some of these controls. You can do things like set the rule-based execution security. You can restrict the namespace it can operate within. You can restrict, for example, the volumes that they can work with. Things like secrets you generally want to give, right? Because applications are going to need those persistent volumes and stuff like that. But you can limit, for example, what they can actually assume. But the downside there is that if you over kind of cast the net here, then you break things and everybody hates security and security doesn't work anymore, right? And our lives continue to suck. The other thing that you have to do, so you can create a PSP and it's like, woohoo, I did all this. And then it's not actually going to work because it uses role-based access control to determine which pods and containers can actually pull that. Container is going to look, so basic just there is that if you haven't applied the RBAC to it, then it's not actually going to apply it at emission to your containers. Because it's going to be looking to apply it based on things like the subjects, the users and the groups that are within it. So another interesting thing we get to work with is sidecars. So sidecars are a cool pattern. Has anybody worked with things like Envoy, Istio in their environment? Has anybody heard of Envoy? It's a Lyft project. It's cool. No? Okay. So Sidecar essentially allows us to decompose things. It allows us to extend what a container can do without actually modifying the container itself. So we generally deploy a Sidecar with a container, which ends up meaning that we also, if we want these things to scale, need a way to actually inject these things automatically. So if we launch a new container, we want it to have a Sidecar, right? So in the Sidecar, we can do things like mutual TLS, so we don't have to worry about our container handling those things. We could do authentication and authorization between services to determine which microservices essentially can call out over the network to other ones. We can offload things like logging. We can do that in the Sidecar. And we can do things if we have these kind of deployed. And we can do things like distributed tracing and have the ability to understand what's happening between our services. Generally, we spend a lot of time and money giving ourselves monitoring abilities at kind of ingress and egress points. And we don't really understand what happens in between. So when we deploy things like sidecars, we get another way to get a lot of intelligence out of our containers. But it requires some way to manage these and get a derived data and context from them if we want them to be valuable. The ambassador pattern is kind of similar. So we work with like an out-of-process proxy. So we can either have, for example, an ambassador per container, or we can have a daemon that our containers kind of sit behind as a proxy, right? So we can have them sit behind HA proxy, something like that. But it's another way that we can also, if we want to update legacy applications and kind of make them cloud native, then we can do things like proxies and ambassadors to kind of phase them in, right? So when I talked about how people do different strategies and they phase out a monolith and they decompose it, see all kinds of strategies, and sometimes one of the answer is putting a proxy in front of things, right? And just kind of hiding certain behaviors and having that translation layer. So service mesh is where it actually gets useful. And so I don't know if anyone's actually heard of Envoy. If not, definitely take a look at it. Consul's HashiCorp's implementation of something similar. But essentially it allows us to actually manage the sidecars, right? So we have a sidecar essentially deployed with each one of our containers. Try to make it as big as I can. Cool. What you can see there, so we have two pods, pod A, pod B, and in front of each container we notice that we have an envoy, right? So we have service A and service B. So the envoy is sitting in front of it, and it's handling things like mutual TLS between services. It's doing things like logging, right? So we have the ability to see kind of all the I/O coming in and out. And then it talks back to, there's a couple different services Istio has. There's Mixer, there's Auth. But what it ends up doing is gives you the ability to kind of aggregate all this stuff, and then you can use different dashboards like Grafana to visualize and kind of understand what's happening in your environment. Unlike service meshes, I think they do add a layer of complexity of their own, especially things like Istio. They're non-trivial in some ways. There's some allure in it, but there's some kind of hidden dragons and implementations. They introduce a lot of new resource types. There is some overhead to management, things like that. But it's a trade-off, right? Because there's things that now we suddenly have magic security controls that we don't have to worry about as we deploy new applications. So automated injection is one of those important things, right? Anytime we deploy an application, we want to make sure it has a sidecar in front of it, right? So we don't want to get in the habit of like deploying applications without sidecars. But if you take a look at how things like Istio and Envoy work with Kubernetes and integrations, they do give you the ability to inject a sidecar when we spin up a new pod, right? So we have some assurance at that point that our pods have things like mutual TLS, because who has TLS everywhere in their environment, including between all of their internal services, right? Like I know big and small organizations that have like plain text traffic passing somewhere, right? And this is one of those things. Do you do this at every single application and manage the key infrastructure yourself? Maybe not. Things you can also get from kind of running a service mesh. You can push policy down. You can push configuration updates. So that sidecar that's running can also get updates to security policy. So you can run it in conjunction with the things you could do with a controller and an emission control. You can also push those policy updates in real time. You can limit egress controls. If you have a compromised service, you can basically get rid of all its keys and revoke those, and you're going to be limited in what that can actually access. And you can manage all that through PKI, which is managed for you. Like I don't say manage PKI, I say let Istio manage it for you. But this is cool because I see this as an opportunity to get rid of things that we spend a lot of time, money, and we still get wrong. Secrets management is another place that we have to think. So we have first-class APIs in most platforms now, but sometimes we don't use them. Or we use them and they still suck. So Docker, for example, on top there, if you were to do that and you run with -E, you're running environment variables, which means those are going to be available with like a set command. They're going to be in different logs and dashboards, right? So this is not the greatest way to distribute credentials. Docker has a secrets management API, and you can do Docker secret create. What ends up happening is people will put those secrets then in shell scripts. They'll put them in other files that go into like GitHub and all these other places, and they're on developer laptops. And so you find that you get a little bit better at it, but you just kind of kick that problem somewhere else. And Kubernetes does have a first-class secrets management API, and I know like Mesos, Marathon, they support secrets management as well. Docker Swarm, pick your orchestration tool. But we still have some problems there, because what we end up finding is that we still store those in plain text. So remember we talked about that etcd that people put on the network with no authentication and full network access, right? Well, everything's stored plain text credential-wise there. So all your application secrets are stored base64 inside of an etcd key value store. So we can encrypt them. And as of like Kubernetes 1.7, they gave you the ability to do secrets encryption at rest. Docker Swarm supports secrets encryption at rest, and there's similarities in all the approaches, but the downside there is you still need a symmetric key to do that, and you have to basically spin that up with that, and then you have to figure out how to get rid of that key at some point. So it's maybe a little bit better, but it still has implementation-related issues that are going to happen. And as I mentioned, what people end up doing is they will put secrets in config files, right? They'll put them in, pick a place the config file is going to end up at, right? So we can integrate with things like key management solutions, and the integration's getting better. So they're not in this slide because I haven't played with it that much, but Vault has the, does anybody mess with like Vault's auto unsealing functionality and integration with like key management? That's, I think, the way to go, to be perfectly honest. Like nobody has any business managing secrets. Key management solutions combined with things like Vault, right? And if that's like a first-class integration, you can rotate secrets, keep them away from people's prying eyes. Basically, the kind of concept here is that if you're using something like Vault, and again, you could work with, I know there's tools like CyberArk, and if you pay for something, great. But essentially what we end up doing at that point is we don't actually store the secret in the kind of orchestration environment, but we need a way to authenticate to something like Vault, or wherever we store those secrets. So we end up using service account tokens. So remember when I also talked about the fact that we want to create accounts that use different service account tokens? So all these things kind of start to follow us as these services need to do things, right? So now we need to access secrets. So imagine we have, gotten those things out of our cluster, and we put them inside a vault, but we're still sharing service counts, right? Well, then it's kind of trivial at that point to be able to steal that service count token because you're running as the same account and impersonate within Vault, right? So we've gotten maybe a little bit better at that point. So all these things, right? Authentication, how do we create our accounts? As you see, these things follow us as our application and architectures evolve. And here's an example if you were going to just like script that out, and you see a lot of things that run curl, and I actually picked that one verbatim. And as you can see, they do it over HTTP, which is fantastic. And but essentially what we end up doing is we have the ability to do some calls before the container actually starts up. So we end up calling out, and we use service count token, unlock, call out to Vault, get those credentials, and then we mount those for the container when the actual container itself's lifecycle starts up. So the container itself doesn't know any better how it got the secret, where it got it from. It just knows that when the container starts, the secret's ready for it to use within your application. And then whatever you do with the secret from there at runtime is up to you, right? I know people that they'll run a script to kind of kill the container secret and make sure, but it's still get it at some point. Cool, that's my presentation, folks. So things I kind of wanted you to think about today are just thinking about the patterns. And what we end up seeing across cloud native systems is that a lot of the same patterns are codified, and a lot of the tools we're picking and pulling off the shelf are adopting a lot of the same patterns. So things like service mesh you're going to hear a lot about. Using things like sidecars you're only going to hear more about. And some of kind of the core things like reconcilers. We didn't talk a lot today about circuit breaking, but circuit breaking is a big thing you'll kind of deal with a lot. And these are all the core patterns to kind of understand as you build and especially secure your systems. One of the things that I've seen is that people's environments are very kind of codified around their workflows, kind of business functions, right? So things like that, right? Related systems are maybe going to related. So you have to think about how does your organization work and how does that actually translate to a software stack. And last but not least, apply security controls at the layers they make the most sense at. Some things make the most sense in your application. Some things make sense in a Docker file. Some things make sense to do with Kubernetes. Some things make sense just let AWS worry about, right? So just kind of always focus on where does it make the most sense and where do you get the most bang for your buck and the least is going to go wrong with implementing those security controls. Thank you everybody for coming today. There's my contact info. Any questions before we jump out of here? Yes, sir.
You mentioned, or you compared and contrasted sidecars to service mesh pattern, and I just wanted to follow up to see how you might contrast those two. The service mesh, like individual little features that you get that are spread around, or how would you contrast?
So his question was, what's the difference between essentially or relation between a sidecar and a service mesh? So a sidecar just basically refers to the fact that you're going to deploy a container alongside another container that's going to offload some functionality, right? So they're going to have some access to shared resources, network namespaces, and stuff like that. But sidecars need some way to manage those, right? And they need some way to communicate with each other and have some centralized way to manage them with policies. So that's where service mesh comes in, because inside of that service mesh, what we end up having is all those sidecars can communicate back to the mothership as well with each other, right? And they can get information. So if we run sidecars in a distributed way, then we want to run those within a service mesh. So the answer to how do you know what your state is? Yeah, it means, you need obviously telemetry. You need understanding, obviously, of what's happening between environments as things are being promoted, right? And unfortunately, there's not like one layer that's all going to happen at, right? In my opinion. So, obviously, one of the things that helps with that is base image management. So, organizations that have here's the base images you're going to extend from, and we at least know these base images have support for things like SATCOM being built in. So, I've seen that handled through image management. Just basically being like, here's our internal, right? You can't basically call out to like Docker Hub. You can only get from like, but at the same time, you can, but we can call those, but we're going to pull those things in. It's unfortunately a multiple layers probably at this point, right? So a lot of unsolved problems. So in terms of sharing service account, there's some things you have to accept that there's some consequences, right? There's some things that are potentially going to be torn down in terms of access to namespaces, right? Because you're going to be same user inside of some of those things. So there's some of those things that are kind of I believe at some point you'll be able, for example, inside of a pod to be able to run with different accounts, right? As opposed to like if you run everything inside of a pod now, you have to run with the same service account. At some point you'll have the ability to do both, right? But in terms of managing, in terms of, so like if you look at different distributions like OpenShift, for example, they solve that problem to a degree, right? Because you'll run with different users when you actually run. Yeah, so I guess the short answer to that is there are some ways you can do that, and different distributions handle it differently. But yeah, stock Kubernetes, there's yeah, a little different. I think I'm probably out of time, so thank you very much, everybody.